Welcome back. Today we're going to start chapter 8. The first topic is arc length. Let's consider the curve y equal to f of x, function or the curve y equal to f of x. Let's say you want to calculate the length of the curve starting from the point A to the point B. That means that if we stretch this curve into a straight line, we want to figure out what is the length of this curve. Normally, if you wanted to deal with the area, if you remember, we would break it into smaller pieces and we continue to do that and calculate each area, then we sum up those areas. We're going to start with the same idea. Let's say we consider a couple of points, maybe point x1 to x2, then x2 to x3. We call this x3 and so on. The closer that we pick the points, then the more accurate our calculation becomes. So let's say you have 2 points x1 and x2 on the curve. So here's x1, here's x2. If we connect these 2 points with a straight line, that straight line is the length of that straight line is not exactly the same as the curve's length, but it's close if you pick the x1 and x2 to be very close to each other. So approximately, we can say the length of that curve from the point P1 to P2 is basically the distance between those 2 points, which is the square root of the difference between the x's squared plus difference of the y squared. So here, y2 minus y1 squared plus x2 minus x1 squared. And you can show that the difference in the x is by delta x. So delta x squared, difference in the y is by delta y. We can rewrite this in a better form and using the idea that we had that if you have intermediate value theorem, that if you have f of x2 minus f of x1, that is the same as the derivative at some point between x1 and x2, where x star is between x2 and x1, some value, and multiply by the difference of x2 minus x1. Then this is just y2 minus y1 equals to the derivative at some point in between and multiply by x2 minus x1. The closer that you pick the x2 and x1, the more accurate the length of the curve becomes. So basically you can say this is the same as delta x2, delta x squared, plus, instead of delta y, this is exactly the same as delta y. This is the same as derivative times delta x. So f prime x star times delta x. So I can write f prime x star times delta x, or squared times delta x squared. And you can factor out the delta x, which is basically becomes 1 plus, if you factor out delta x squared, and you can deal with the square root, so f prime x squared and delta x outside. The square root of the delta x squared would be simply delta x multiplied. And if you remember, when we calculated the area under the curve, we said the closer you pick x1 and x2, the more accurate the assumption becomes. So basically, this length, if we add up all those lengths, we can write this the next year, which means sum of all these derivatives multiplied by the delta x. So assuming, this is basically the idea. So assuming, this theorem gives you the arc length. Assuming we have a continuous function over the interval a to b, the length of the curve for the function y equal to f of x from over the interval a to b is basically calculated by that summation. The summation of all those derivatives squared plus 1, take a square root. So basically, if we integrate from a to b of the square root of 1 plus f prime x squared dx, we get the arc length. And sometimes instead of f prime x, you can write dy over dx. It's the same thing. This is assuming that y is a function of f of x. Sometimes you have x equals to f of y. So then instead of dy over dx, you have dx over dy, the other way around. Okay, so let's try to use this to calculate some arc length. Here, for example, find the arc length of the curve y equals to square root of x cubed over the interval 0 to 1. So I can say the arc length by itself, there's a notation for it, but I'm going to use the L, is the integral from a to b, in this case from 0 to 1, of the square root of 1 plus f prime x squared dx. So what do I need? I need to assume that this is y equal to f of x. We need to figure out first what is dy over dx, or f prime x. And f prime x, this is x to the power 3/2, so the derivative would be 3/2 square root of x, or x to the power 1. So if I replace it in the integration, this becomes 0 to 1 square root of 1 plus 3/2 square root of x squared dx. Can simplify this a bit. Becomes 0 to 1 square root of 1 plus 9 over 4 x square root, and square root cancel out dx. And now the question becomes, how do you integrate this? And simply you can use substitution. Say u equals 1 plus 9 over 4x, then du equals 9 over 4 dx, and therefore dx equals 4 over 9 du. And you can update the boundaries. You can say u equals to what if x equals to 1, u becomes 1 plus 9 over 4 times 1. This is assuming if x equals to 1, which is u equals 13 over 4. And if x is 0, then replace 0 into the equation for u, and you'll get u equals to 1. So I can update the boundaries from 1 to 13 over 4. Sorry about that. And instead of square root of u, instead of dx, I can write 9 over 4. 4 over 9 d. And simply this integral becomes 1 to 13 over 4 times 4 over 9, not times, 4 over 9 u to the power 1/2 d. Integrate this, 4 over 9 multiplied by the integration of that, u to the power 3/2 divided by 3/2, which is the same as 2/3 times u to the power 3/2, and evaluate it from 1 to 13 over 4. That is 8 over 27 multiplied by 13 over 4 to the power, so 13 over 4 to the power 3 minus 1 to the power 3/2, which is simply 1. And if you have a calculator, you can calculate this, but this is the length of the curve over the interval 0 to 1. Okay, so basically if you find the derivative, then it's nothing more than calculating the integral. And for that, you have learned the integration techniques. You can use those. Here's another example. Find the length of the curve. X equals 1/2 y squared over the interval. You notice that here it's not y equal to f of x. This is not the case. What we have is x equals to f of y. So basically, y and x is changed, which means the curve we wrote in terms of y, not in terms of x. There are two cases you can change this to and rewrite in terms of x, or you can simply assume that if you want to calculate the arc lengths, I'll say from a to b, square root of 1 plus, instead of dy over dx, I write dx over dy. Because now x has been represented in terms of y squared dy. Remember, the original integration is if you have from a to b square root of 1 plus dy over dx squared dx. This is assuming that y is a function of x, when in this case x is a function of y. So we changed every y and x together. And then I need to figure out what is dx over dy. This becomes simply y. All right, take the derivative, it's y. So the integral becomes from 0 to 1 square root of 1 plus y squared dy. And this integration actually requires substitution. Trigonometric substitution. Y equals tangent theta. So then dy equals secant square theta. And you can update the boundary. If y equals to 0, then theta would be 0. If y equals to 1, then since tangent theta would be equal to 1, it means theta must be pi over 4. Then this integral becomes integral from 0 to pi over 4, square root of 1 plus tan square theta times secant square theta d theta. D theta. And you can simplify this. 1 plus tan squared is the same as secant, so this is from 0 to pi over 4. Secant theta times secant square theta d theta. I think we've done this already in the earlier sections, in the trigonometric section. Secant cube theta d theta. But if you don't remember, I think the idea was to use integration by part. We assumed that we wrote this in terms of secant theta times secant squared, which I can erase this because we already have it in that format. We use integration by part. We assume that let me use different color. We assume u equals secant theta, and dv is given as secant square theta d theta. Therefore du would be secant tangent. Du equals secant theta tangent theta. V equals tangent theta. If I'm going too fast, it's just because we've done this in the trigonometric section. But I'm just going to make sure that everyone knows. So here, if we have u dv, then we have u times v, which is secant theta times tangent theta, plus, minus the integral of v du, which becomes secant theta tangent, so it becomes secant theta tangent theta times secant squared v du, so times tangent, so it becomes tangent squared d theta. And 0 to pi over 4. Let's ignore the boundary for the moment till we calculate the integral, because we have to evaluate this at 0 to pi over 4 as well. So 0 to pi over 4. That is the same as secant theta tangent theta minus this integral. You can write the integral from 0 to pi over 4. Instead of tan squared, you can write 1 minus secant square theta d theta. And we can do this. Secant theta times tangent theta, 0 to pi over 4 minus the integral of secant theta times d theta from 0 to pi over 4, and negative, I'm distributing this into both of them, so it becomes plus 0 to pi over 4 sorry, it is positive secant minus 1. There we go. This is supposed to be minus here, plus there. I forgot a negative there. Okay, so plus minus secant cube theta d theta. And if you remember, this is what we started with on the left side, and on the right side we ended up with the same thing. So if you move it to the other side, basically you get two of them. So I can say the integral from 0 to pi over 4 secant cube theta d theta is the same as 1/2 secant theta tangent theta from 0 to pi over 4 plus the integral of 0 to pi over 4 secant theta d theta. And again, here, this integral showed up exactly on the other side of the equality. And what we know that if we move this integral to the left side, you get two of them, so you divide it by 2, so here is what that 1/2 shows up. And so you can integrate this, the other integral as well. This is one of those theorems that we calculated the integral of secant. If you remember, I wrote it as a note. So plus the integral of secant was ln secant theta plus tangent theta. Evaluated from 0 to pi over 4. So let me evaluate everything at the end. 0 to pi over 4. Okay, so here finally this becomes 1/2. If you replace pi over 4, secant of pi over 4 would be 1 divided by cosine of pi over 4. That is root 2 over 2. So flipped over would be 2 over root 2, or just simply root 2. Times tangent is 1 plus ln 1 plus root 2 minus, if you replace 0, tangent would be 0 in both cases, so you get root 2 times 0 plus ln root 2. Which basically simplifies to 1/2 root 2 plus ln 1 plus square root of 2 minus ln square root of 2. No need for the absolute value since these are positive values. Maybe use parentheses here. Okay, so even though it's not that nice, but it is a solution. Okay, so it took a long time to calculate the integral, but we found a number that represents the arc length. Okay, so these are our arc lengths over interval, but similar to the derivative at a point gives you the tangent line, the slope of the tangent line. The arc length, you can extend the arc length starting from a point to any other point as a function, represent the length as a function. So that function is if it's from a to b, we would write integral from a to b. But if you assume that the end of the length of the curve, so let's say you have a curve, you want to start from here, a, up to that point would be b. But if you let the length of the curve be at any point, so if I ask you at the point x1, for example, you just let the b to be the x1, or basically we can let this endpoint vary and say find the arc length from this point up to the next one. We call that endpoint to be x. And you can calculate the integral exactly the same thing. So the arc length function, this is what we call the arc length function. It gives you, starting from the a up to x, the integral of 1 plus f prime. It's not supposed to be x because x is the variable in the boundary. So f prime of t squared dt. It's no different than calculating our length from endpoint a to b, but in this case we assume the b is a variable. Here's an example for you just to see. So find the arc length function for the curve. So the result is a function. It's not a constant. It would be a variable depending on x. For the curve this, let's say starting from x0, x equal to 1. Sorry. Here, arc length of function for the curve when a equals to 1. Okay, so what we do is we always need the derivative, so I'll figure out what is y prime. It will be 2x minus 1/8 times 1 over x, or 1/8 over x. Okay, so the arc length becomes as a function, so sx, I'm going to write integral from 1 to x, square root of 1 plus the derivative squared, but the derivative we should represent in terms of another variable, not x. So I'll write it as 2t minus 1 over 8 squared dt. And this is 1 to x square root of 1 plus 4t squared minus what is that? 2t times that, it becomes minus 1/2 plus 1 over 64t squared dt. And you may ask me, why did you square it? Here's the reason. If you calculate this under the square root, it looks exactly the same thing, 4t squared plus 1/2 plus 1 over 64t squared. And it turns out that this is, under this square root, is exactly the same as, let me write this, it's exactly the same as 2t plus 1 over 8 squared. And sometimes the trick in this example is that to notice that if you add 1 and negative 1/2, you'll end up with positive 1/2, which is exactly the middle term of that squared form, dt. And now the square root can cancel out 2t, since we assume positive values, 1 over 8t dt, and integration becomes very simple. It will be t squared plus 1 over 8 ln t. So if we evaluate from 1 to x, what we get is x squared plus 1/8 ln x, and if you replace 1, it would be minus 1. ln of 1 is simply 0, so minus 0, which basically tells us that the sx is x squared plus 1 over 8 ln x minus 1. That is the arc length function. And if they ask you what is the arc length of this function from a to b equal to 2, then you just simply replace 2 for x and say, okay, what is the length at 2? It will be 4 plus 1/8 ln 2 minus 1. this would be the arc length over the interval 1 to 2. Okay, so if you find the arc length function, then basically you can figure out the length over any interval. Okay, so here, this is where I'm going to stop. Next time. Hopefully we'll start talking about the area of surface over revolution. But here, this is basically the arc length. Try a couple more examples. The examples are very similar, and it's quite easy. Actually, the only issue is to calculate the integral properly.